In this lesson, we will study eigenvectors and eigenvalues. So what are they? Well, an eigenvector of an n by n, so we're looking at square matrices. An eigenvector is a vector x that is non-zero such that ax is equal to lambda x for some lambda, and lambda is just a scalar. In addition, the scalar itself is called the eigenvalue if there is a non-trivial solution x for that equation, ax equals lambda x. So before we look at, making sense of all of this, let's make sure we understand graphically what's happening. So if I have some vector u, or I guess I could have called it vector x, essentially what we're saying is that lambda is going to be some scalar, which might make u compress a little bit, or stretch, or possibly go in the opposite direction. And so essentially lambda is going to create our resulting vector somewhere along that line. So now let's take a look at mathematically, what does this do for us? The first thing we can do is to determine if x is an eigenvector of A, and they've given us an x vector. So I have A is 2, 3, negative 1, 6, and my question is x, 3, 1, an eigenvector of A? So all we have to do here, if you'll recall, we said that ax had to be equal to lambda x, and so I'm going to take ax and see what happens. In this case, that's 2, 3, negative 1, 6, and then 3, 1. And we all know how to multiply matrices. So I'm going to get 6 plus 3 and negative 3 plus 6, and that gives me 9, 3. So ax is 9, 3. The question is that equal to some scalar times x? Well, I can see that 9, 3 can be written as 3 times 3, 1, and 3, 1 is actually just x from the question. So is x an eigenvector of A? Absolutely, because 3 is my eigenvalue, and I can take 3 times x, and that is equal to ax. So it really just fits the definition. So that's how you're going to determine if some vector is an eigenvector, is you're just going to multiply a times x and see if it's equivalent to some lambda times x. Let's look at another question, and this one again is using my same matrix A, but I'm asking a different question. I'm asking to determine the eigenvalue of A for x, which in this case is 1, 1. So in the last question, I was asked to determine if a vector was an eigenvector. Now I'm asking to find the eigenvalue, if one exists. So it could be that I ask you to find the eigenvalue and it doesn't exist. But in this case, obviously, I'm not going to do that. But the good news is we're going to do this the same way that we did the last question, because I'm still saying that if an eigenvalue exists, then it's going to, then a times x is going to be equal to lambda times x for some lambda. And of course, the eigenvalue is just lambda. So all I'm going to do is exactly what I did on the last question. I'm going to take A, I'm going to multiply it by x, and that's going to give me, in this case, 2 plus 3 and negative 1 plus 6, and that gives me 5, 5. And just like I did last time, I'm saying, is 5, 5, are we able to write that as some scalar times vector x? And of course, this is 5 times 1, 1, which is 5 times vector x. And therefore, the eigenvalue lambda is 5. So we could have easily been asked, is x an eigenvector? And we would say yes. Or what is the eigenvalue? And the eigenvalue is 5. Let's do a practice now that's just a bit more difficult. And again, we're still using that same equation that says AX is going to equal lambda X if lambda is an eigenvalue. And of course, that's what we're trying to do, is show that some value is an eigenvalue. Now, I've already done a practice like this in the opposite order. So our very first practice, practice 1, actually used the same matrix A, and instead it gave me a vector and said, is this an eigenvector? And then we had to solve to find an eigenvalue. This is the opposite of that. So here I'm giving you an eigenvalue, and we already know in this case it's an eigenvalue because we did practice 1, but typically you won't know that and you would have to show that it was true. You might be asking, how do we do that? Well, I'm glad you asked. We're still using this equation, and we're going to say, well, if that's true, then AX minus lambda X must be equal to 0. And then I could say, well, A minus lambda X is equal to 0. But can I really take A, which is a matrix, and subtract lambda, which is a scalar? No, I can't. So what am I going to do? I'm going to take lambda times the identity matrix. So for obviously a 2 by 2, my identity matrix is 1, 0, 0, 1. So here's how this is going to work. I'm going to take A, which is 2, 3, negative 1, 6, and I'm going to subtract lambda, which is 3, times the identity matrix. So I'm going to take 3 times the identity matrix and get 3, 0, 0, 3. And I'm going to subtract this. So 2 minus 3, negative 1. 3 minus 0 is 3. Negative 1 minus 0 is negative 1. 6 minus 3 is 3. So you might be asking, okay, great, but what am I looking for? Well, if you'll recall, our original definition said that the scalar is an eigenvalue if there is a non-trivial solution. So let's remember that if I end up, like I do here, with a free variable, because what's going to happen? I'm going to reduce this by making this positive 1, negative 3, and then I can obviously get 0, 0 here, which tells me that x1 is a pivot and x2 is free. Why is this important? Because if I ended up with the identity matrix, then that would tell me that I had only the trivial solution. And if I have only the trivial solution, then it's not an eigenvalue. And that's not what I have. What I have is a free variable, and when you end up with a free variable, then obviously we have a non-trivial solution, and therefore it's an eigenvalue. So what I've done so far is answer the first part of this question that says show that 3 is an eigenvalue. And by doing these calculations and finding that I have a free variable, I have shown that in fact 3 is an eigenvalue. The next part of this question says find the corresponding eigenvectors. So not a lot more work here, and in fact work that we're quite used to. This row says, and again, I didn't augment the matrix with 0, and if you look in your textbook, it does in fact show the 0 column vector for the augmented matrix. But what this is telling me is as x1 minus 3x2 is equal to 0. So again, we're very used to this. We know that I can describe my solutions by writing x1 and x2, and that would give me x1 is actually, by moving that to the opposite side, 3x2, and x2 is x2, and I can factor out my x2, and I would get 3, 1. So here's what I have. This is an eigenvector, and This is for specifically the eigenvalue of 3. The question says find the corresponding eigenvectors. So the corresponding eigenvectors are all vectors in this form. So I wouldn't list all of the eigenvectors, well, because I can't. I can only say that they're all in this form. But I want you to think about what this looks like. First of all, 3, 1 is right here. And x2 is obviously a scalar, so they're saying any value I plug in for x2, multiply that by 3, 1, and then I would end up with some other eigenvector. So what if I plugged in 2 for x2? Well, that would give me 6, 2. Where is 6, 2? Well, it's over here. Notice it's on the same line. What if I plugged in -1? Well, that would be -3, -1. Where is -3, -1? Why, it's on the same line. And I could continue that for any values of x2, and what's going to happen? I'm going to end up with values all along that line. This line, and notice that it goes through 0, 0, which is important, is called the eigenspace. And again, it's the null space and the subspace of Rn. So this is just a subspace, and it's all the values along this line going through that point 0, 0, or 0, 0, 0, 0, however many zeros you need. This obviously is two-dimensional. I do also want to point out that when we did questions like this before, we might be asked to find a basis. Well, that's really what I have done already. This is obviously a 2 by 2 matrix, and when I'm finding the basis, which I have already done the work for, it's just going to be that 3, 1. And if you'll notice, I have one vector for a 2 by 2, and it makes perfect sense for that because I have a free variable. So it wouldn't make sense to have 2 vectors in a 2 by 2 matrix unless, I was having only the trivial solution, which would mean it wouldn't work anyway. So you should always have one fewer. Let's try another question where we are asked to find the basis. And again, this one is a 3 by 3 matrix, and we are given, again, the eigenvalue of 2. And we are asked to find the basis for the corresponding eigenspace. So again, all I'm going to do is use that same formula, a minus lambda I x equal to 0. So in this case, that means for -1, 6, 2, 1, 6, 2, -1, 8, subtracting 2 times the identity matrix, so 2, 0, 0, 0, 2, 0, 0, 0, 2. Subtracting gives me 2, -1, 6, 2, -1, 6, 2, -1, 6. Doing row operations, obviously, I end up at 2, -1, 6, 0, 0, 0, 0, 0, 0. And I could continue further to get 1, -1/2, 3, 0, 0, 0, 0, 0, 0. Which means, of course, that I can write this as, we have x1, x2, x3, we have x1, and then my free variables are, of course, x2 and x3. which means I can write x1. I'm just going to go straight to having x2 and x3 on the outside. So x1 can be written as 1/2 x2 minus 3x3. And then, of course, x2 is x2, and then 0x3, and x3 is x3. So again, the question says find the basis. So what I have done is write it in its general form, which means my basis is those, I keep forgetting to put those brackets, is 1/2 1 0 and -3 0 1. And again, just as we talked about last time, this is a 3 by 3 matrix, but notice I'm only going to have 2 vectors in my basis. I do have this one last practice for you to try on your own, but before you do it, I just want to point out that section 5.1, I've really broken it into 2 parts. This video that you're watching now is the very practical, here's how you actually do it video. The next video is the more theoretical video, so we're going to be looking at a couple of theorems dealing with eigenvectors and eigenvalues. So back to this question. This should be very similar to the last 2 questions that we did. I want you to show that lambda equals 2 is an eigenvalue or show that it is not. Once you are done, press play to see how you did. So no surprises here. I'm using an eigenvector, an eigenvalue of 2. And I'm going to take a, which is 7, 3, 3, -1. I'm going to subtract 2 times the identity. So again, I've got a minus lambda I x equal to 0. So I'm taking 2, 0, 0, 2. 7 minus 2 is 5. 3 minus 0 is 3. 3 minus 0 is 3. And -1 minus 2 is -3. And I should be able to stop right here because it's very clear to me that I can start doing some row operations, and I'm going to go ahead and reduce this. But hopefully at this very first point, before I ever do row operations, you can see that I'm not going to end up with a free variable. But in case you can't, that's okay. Let's add rows 1 and 2 together. That's going to give me 8 here and 0 here. And I'm going to do a row swap because I want my first value to be 1. So I'm going to now take 1/8. So I'm doing a scalar. So I have 1, 0, 5, 3. I can take -5 times row 1 and end up with 0 and -2. I'm sorry, just kidding. 0 and 3. And then I can do 1/3 of row 2 and end up with 1, 0, 0, 1. But again, hopefully when you got to this point, you could see what the outcome was going to be. But even if you couldn't, what I've ended up with now is the identity matrix. Now, if you'll keep in mind what we did before, I had a free variable before, and the free variable before told me that I had more than just the trivial solution. This guy is the identity matrix, which means I have only the trivial solution. And what does only the trivial solution tell me? That lambda equals 2 is not an eigenvalue for matrix A.